Gang, in the 802.11n or AC standards, you've got a lot of technologies that give us better throughput, right? There's a reason why we're using these technologies instead of sticking with 802.11 A, B, or G. What are those technologies and what does it look like to ramp that up? Well, we're not going to go into too much detail on the technologies right now, but just to give you an idea, first we've got channel bandwidth. And so instead of using one channel, if we use two adjacent channels, then we get, whoa, double the bandwidth. If we used 4 adjacent channels, we get 4 times the bandwidth. It's just straight up, you're using more of that signal range. And technically, it's even a little bit more than that because normally there's a little bit of space between these channels that's used as a buffer. Well, those spaces can now be used as data carrying subchannels for this overall range that's now 40 or 80 megahertz wide. Spatial streams, all right? It's great if you have one antenna, but what if you had multiple antenna and those could send out different signals using different angles of attack between the one location and another, maybe between different access points. They're able to send different streams simultaneously. That's more effective. Again, greater bandwidth, higher degree of modulation. So we've got this signal that we're sending, and we have the ability to encode the peaks and valleys and the polarization, the magnetic field. We're able to come up with symbology that represents that using orthogonal frequency division multiplexing. And so using the different methods, we can stuff more data inside those frequencies, make them mean more by interpreting them in a more sophisticated way. So that's our modulation. Shorter guard intervals. In between effective data sending, we have kind of some buffer space. That buffer space is not effective communication. So instead of having a long guard interval, if we shorten that so that our buffer space between sending and receiving frames is shorter, we are going to be able to send more data over the same line. And then MAC efficiency. Last thing here is, okay, what if we aggregated several pieces of data together and acknowledged that one time instead of acknowledging each individual frame of data that came in? That would be more effective and use fewer acknowledgments on the wire. So I'm going to send 3 things. Okay, I got 3 things. We're good to go. That's more effective than send it, got it, send it, got it, send it, got it. That's MAC efficiency, using the wireless network less often so that you can spend more of your time sending data. So N and AC all use these technologies to greater and greater degrees as we move from N to AC wave 1 to AC wave 2, right? That's a continuum of improved operation. Let's take a look at it. So we go back to the original standard 802.11a, 20 megahertz, one stream, an old modulation rate, long guard interval, 54 megabits per second physically, and only 24 of throughput. Half of our signal is essentially lost just to overhead. That's bad news. So as we move to N, as we look at the minimum and maximums of N, again, what we're doing here is supporting greater and greater degrees of maybe increasing the bandwidth, increasing the number of streams. We're using actually the same modulation mechanism throughout all of it, using short intervals instead of long intervals, so less buffer. And so you can see we just keep increasing our physical data rate and our overall throughput. And notice we're not losing half. We're losing only about a quarter at this point, or a third or a quarter to the process of communication itself, to the overhead. But it gets better. When we move to AC rather than N, this is wave 1 AC, we've got 80 megahertz channels that are now available. Our spatial streams can go from 1 to a theoretical 8, although in implementation they only go as high as 3. And so, and again, we go from long to short rates. Notice we're actually changing to a different constellation size and rate. We were using the 3.4 64 QAMR. Now we move from 64 QAMR 5.6. So again, increasing that value. And then we move from 64 to 256. So a more complex encoding mechanism, more vulnerable to failure though. If there's corruption of signal, you are more vulnerable with the new AC protocol. It is something to be aware of. But our data rates, they just keep on climbing, all right, to our high-end products having 1300 and 910. As we move to 802.11 AC Wave 2, Well, now we can have 160 megahertz wide channels, 1 to 8 with an ultra high end product, expected to be 4 spatial streams sporting multiple user MIMO. Got our advanced modulation technique, we got a short guard interval, and look at that, man. 2.4 megabits per second of effective data throughput. That's huge. And that's exciting because that means we can really use this to replace a wired network in many situations just as effectively and supporting a decent number of users at the same time.